So in this analogy, that's what we have to try to find. So how do we try to find it? Let me turn now to the experimental setup, the accelerator first. So the Large Hadron Collider at CERN is the world's most powerful particle accelerator. As I said, we accelerate protons, so we have counter-circulating beams of protons in opposite directions, and then we smash them head-on, again, to try to free up as much energy as we can. So it's like two Mack trucks colliding on the highway in a head-on collision. That frees up a lot of energy. That's not such a good thing to happen, but in our experiments it's very good. We free up a lot of E, and particles can materialize from that energy. So the design energy of this accelerator is 14 TeV, that's 14,000 GeV. Remember, 1 GeV is the mass of the proton. Or another way to think about this tunnel, which you see here in this aerial shot, the red ring, is marking the position of the LHC in Geneva. This is the Geneva airport to sort of set the scale. This tunnel is 17 miles around, about 100 yards underground. The protons at this energy go around that ring more than 11,000 times per second, going at 99.999999% of the speed of light. Okay, so they have very high energy. That's very important, obviously, because of E equals mc squared. The other thing that's very important is we need really intense beams. We have to produce a lot of collisions. The reason is, as most people probably have heard, quantum mechanics, which is governing all of this, is a probabilistic theory. There's the old expression from Einstein that God doesn't like to play dice. Turns out he does like to play dice. Nature is probabilistic, actually. Einstein was wrong about that. And so the standard model, or indeed any model, the final model, if we can finally get there, cannot ever tell you what will happen in a given proton-proton collision. All it can tell you is what's the probability that this might happen, or that might happen, or this might happen, or that might happen. And so if you want to look for the ones you're interested in, you have to make all of them and then find the ones that you're interested in. We're looking for rare processes. I'll give you an idea of how rare in a moment. So what we do is we circulate two beams of very intense beams of protons, and we produce about 1 billion collisions per second. So we designed and built this over a long period of time. The very exciting news was we started taking data not so long ago. So we ran in 2010 at rather low intensity, and then much higher intensities in 2011. This was at 7 TeV, so half of the design energy. In 2012, we increased the energy a little bit to 8 TeV and ran at even higher rates, and the Higgs discovery was announced in the middle of 2012, so I'll come back. So that's the data we have. This period is now called run 1 of the LHC, that 3-year period. And then at the end of 2012, we shut down to go into maintenance, and in fact to upgrade the accelerator to get from 8 TeV to near this 14 TeV. So we're trying to get to the full energy. Again, E equals mc squared, so energy is king. So the very exciting news is run 2, as it's now called at the LHC, began very recently, so on June 3rd of this year, and we are now currently operating at 13 TeV. Okay, and we'll do so. We'll run basically continuously for the next 3.5 years before we enter another maintenance period. So, big accelerator, has a very big detector, very big collaboration that built it. So our experiment, as I mentioned, is called Atlas. Here's a world map showing where the collaboration comes from. And to give you some numbers, it was built by a consortium, a collaboration of 38 countries. We have now over 3,000 scientists working on this experiment together. And we have 1,000 graduate students. These are PhD students. Okay? There's a competing experiment of a similar size, similar number of graduates. These are enormous sociological experiments as well as scientific experiments. So it's a very exciting place to work. Every meeting you're in, there's people from 10, 20 different countries all working together towards a common goal. It's really rather astonishing. So something about our detector. So this is a picture of the detector. So you immediately notice two things. One that's blue. That's not really blue. And the other is big. Okay, which it really is. This is you coming to visit us sometime. So I give you the dimension. So you can see it's basically a cylinder, 143 feet end to end, 81 feet in diameter, and it weighs about 7,000 tons. I'll show you some pictures in a moment. Before I do that, let me show you an animation where you'll see one of these collisions happening, and we'll also show you a little bit about how we get the beam there. So I'll talk you through it. So we start with protons we get from hydrogen gas. We accelerate them linearly, and then through larger and larger circular accelerators, which are from previous generations of experiments at CERN. This one is the one that discovered the W and Z bosons back in 1983. And then finally into the big LHC ring, going in the two opposite directions. Now we'll go down into the tunnel. So here you see this equation you might recognize. These are superconducting magnets that steer the beam. We cross from France into Switzerland and show our passport. We're in the beam line. Here's a cartoon of one proton with its 3 quarks bouncing around, going in one direction. Of course, we don't have one proton, we have many, many billions, but we'll focus on these two. One's going to come the other way. Here's our detector, and they're going to hit in the middle. Boom! Oh, sorry, sound effect. And here's stuff that comes flying off. And so what we do is we measure all this stuff that comes flying off. These are tracks of charged particles. And these squares, yellow and green, show energy depositions from other particles. So what we do is we measure the energy and momentum of all these particles that come out and hit our detector. And then using the laws of physics, we try to understand what happened in the collision. Okay, so someone has described this as, if you want to know how a Swiss watch works, you take it out and you put it on the floor, and then you smash it with a very large sledgehammer, and you very carefully measure all the pieces come flying out, and then you try to figure out what was going on before. A little more detail, but just as a cartoon, this is now a slice of that Atlas detector. So the beam now is coming into the screen in this pipe, which is evacuated.